Hello, hello. Okay, so we've got a new kind of coordinate grid here that we're going to be working with today. We're working with polar coordinates. And if you've never seen these before, well, they may kind of make your head spin in circles a little bit. But I'll give you a quick introduction to polar coordinates and then show you how they correspond to rectangular coordinates. So we'll be converting between rectangular and polar coordinates today, and we'll even be able to take some derivatives. We commonly use the rectangular or Cartesian coordinate system as our graphing tool of choice. Rectangular coordinates, what you're used to, are in the form of x, y. The equations corresponding to these graphs are either in rectangular form or, as we've been learning, parametric form. However, there are some problems in mathematics that are easier to analyze in a polar coordinate system. Here's a polar graph. So let's just get to know that a second first. It's much like the unit circle in that it starts at 0 and goes all the way around, and it takes 2 pi to do that. Now, there are these concentric circles here, and those represent a distance from the origin. In polar coordinates, a point in the plane is defined by a pair of numbers, r and theta. The number theta measures the angle between the positive x-axis, called the polar axis, and a ray that passes through a point. The number r measures the direct distance from the pole or origin to the point P. So let's see what that looks like. The first one is 4 2 pi over 3. So let's look at the 2 pi over 3 first. And that's an angle coming from the x-axis all the way to 2 pi over 3 right here. And then the 4 is a distance from the origin. And we'll say each of these circles represents 1. So let me clean this up a bit. So on the 2 pi over 3 line, we're going to count 1, 2, 3, 4. Right there. So our A point is 4, 2 pi over 3, and there it is. Okay, B, we've got 7 pi over 6. So for this one, we've got to go all the way around to 7 pi over 6 and then count 3. 1, 2, 3. There's B. C, we're going all the way to 5 pi over 4. So where's that? All the way around 5 pi over 4. But what's interesting on this one is our distance is negative. So if I extend the line going all the way across the circle, the negative distance goes to the other side of that line. So we've got 1, 2. There's C. And then 2 negative pi over 6. Well, that's not too bad. Negative pi over 6 is right here. Same thing as 11 pi over 6. And we'll just count 1, 2. And there's our D coordinate. Now it's important to be able to go back and forth between polar coordinates and rectangular coordinates. So again, rectangular coordinates come in the form of x, y, and polar coordinates come in the form of r theta. Now on this polar graph over here, I've got on the x-axis, well, a distance of x, and going up a distance of y. And the hypotenuse of this triangle that I'm forming is r. So I've got this lovely right triangle, and from the perspective of my theta here, what is cosine? Cosine is adjacent over hypotenuse. So cosine theta is x over r, which means I can take this r and multiply it over. I know that x equals r cosine theta. Well, we can do the same thing to figure out what y equals. So from the perspective of theta, sine of theta is opposite over hypotenuse. So that's y over r. And if I multiply the r over, I know that y equals r sine theta. So I've got what x and y equal. Well, what about r and theta? Okay, now let's look into tangent theta for just a moment. Tangent theta is opposite over adjacent. So to figure out what theta is, I can take the tan inverse of both sides, and I've isolated theta. All right, so that just leaves us with what is r? Well, back to our triangle over here. Using Pythagorean theorem, I know that x squared plus y squared equals r squared. So r, then, is the square root of x squared plus y squared. So this little chart here is going to be our key to going back and forth between polar and rectangular forms. Let's practice. Convert 5 pi over 6 to rectangular coordinates. Okay, so we need an x and we need a y. Well, we know that x is r cosine theta, and we know that y is r sine theta. Let me just plug it in. We have r cosine theta and r sine theta. And then we can just evaluate those. So the cosine of 5 pi over 6 is negative root 3 over 2. The sine of 5 pi over 6 is 1/2, and you can clean that up a little bit. And we have an xy coordinate of negative root 3 over 1. So that was polar to rectangular. Let's go the other way. Here we have an x value and a y value. We need an r. Well, I know that r squared equals the square root of x squared plus y squared. It's the square root of 18 or 3 root 2. Now theta, remember to isolate theta, I just need to take the tan inverse of y over x. So that's the tan inverse of negative 3 over 3, tan inverse of negative 1. So where is tan inverse negative 1? It's at either 7 pi over 4 down here or negative pi over 4. So when we convert this to rectangular form, we could say that this r theta is root 3 over 2, 7 pi over 4. Or we could say it's 3 root 2 negative pi over 4. Or if you want to get really crazy, see, yeah, you could extend this line here, and it could be negative 3 root 2, 3 pi over 4. Look how flexible these polar coordinates are. Now let's move into equations. Convert the following equation to polar form. Well, we have this line, y equals 4. What would that look like in polar form? We know that y equals r sine theta, which equals 4. So r sine theta equals 4, or r equals 4 over sine theta. If you want to clean that up a little bit, 4 cosecant theta. Now part B, x squared plus y squared equals 25. That's the equation of a circle in rectangular form. What would that look like in polar form? Well, we know that x squared plus y squared equals r squared. So we know that r squared equals 25. So r equals 5. And that's true, right? We have the equation of a circle with a radius of 5. And that's what it says here. Example 5, convert the following equation to rectangular form and then sketch the graph. All right, so r sine theta equals 3. What the heck does that mean? Well, r sine theta, that's right here. That's y. So y equals 3. Okay, so that's just a line. What about r equals 2 cosine theta? That doesn't really match anything I've got over here in my little cheat sheet or table. So what could I do to make a match? I don't have an r equals, but I have an r squared equals. So what if I multiply both sides by r? Then I get r squared equals 2r cosine theta. Aha. What is r cosine theta? That is x. So I could just put an x right there. So r squared equals 2x. And I know that r squared equals x squared plus y squared. So x squared plus y squared equals 2x. Oh my gosh, this gets complicated fast, doesn't it? Okay, now what the heck do we do from here? Let me clean this up. And then I need you to take a deep breath. How do we graph this? Well, to graph this, we're going to do this cool thing that I know you've seen before called completing the square. So I'm going to take this 2x, okay, and subtract it over here. And then I get x squared minus 2x, and I'm going to leave this space here, plus y squared equals 0. Okay, now we're getting somewhere. And you remember completing the square, we take this term here, cut it in half, and square it. So that gives us a plus 1. Well, if we do a plus 1 on the left side, we have to do a plus 1 on the right side. Now this, let's clean that up a little bit. That gives us x minus 1 squared plus y squared equals 1. And that's a circle with a radius 1, but just moved over to that center point there. If you're looking at that and thinking, oh my gosh, I would never have come up with that on my own, that's okay. This is a learning mode situation. We're teaching you. Okay, what about this one? Theta equals 2 pi over 3. Well, I need to get an xy out of it, so let's use this one here. If I take the tangent of both sides, I get tangent theta equals tangent 2 pi over 3. Now the tangent of 2 pi over 3 is negative root 3. And then the tangent of theta I know is y over x. So I know that y over x equals negative root 3. So y equals negative root 3x, and that's a line. Again, would you have thought of that on your own? Maybe not, but we're in learning mode here. So I'm just teaching you some different tricks. Now, of course, we're not done until we found the slope of a tangent line. So to find the slope of a tangent line to a polar graph, r equals f of theta, we can use the facts that x equals r cosine theta and y equals r sine theta together with your favorite product rule to find dy dx, which is dy d theta over dx d theta, or maybe simpler, y prime over x prime. Okay, this one is a lot of writing and it's a lot of patience. So just stick with me. Pause the video if you need to, and we'll show you how this works. For example 6, we're going to find dy dx at a particular value of theta. And what we know on the polar curve is that r equals 3 plus 2 sine theta. And we're curious about what's happening at pi over 6. What's the slope of the graph there? Now remember, we need to find y prime over x prime. So y equals r sine theta. So to find the derivative of that, look, we've got two functions being multiplied together. Well, what is r? R is 3 plus 2 sine theta. So I'm going to rewrite this as 3 plus 2 sine theta times sine theta. Then to find the derivative, I need the product rule. Okay, so derivative of the first times the second plus derivative of the second times the first. And I'm going to evaluate that at pi over 6. So cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. And then if we clean that up, I know that y prime of pi over 6 is, after a lot of algebra, 5 root 3 over 2. That's y prime. Now we get to do the same thing for x prime. Again, we know that x equals r cosine theta. We have two functions being multiplied together, and we know what r is. So I'm going to take r and plug it in. And then I'll use the product rule to find the derivative of x. So derivative of the first times the second plus derivative of the second times the first. Now we need to evaluate that at pi over 6. So cosine pi over 6 is root 3 over 2. Sine pi over 6 is 1/2. And then just keep cleaning that up for a negative 1/2. And that is x prime. We'll put all that together for y prime over x prime. Clean that up a little bit. We get negative 5 root 3. Of course, right? Clearly, simple as that. Unfortunately, finding the slope of the graph of a polar curve it's long and it's tedious, but you get some good practice of the product rule and you get some good practice of your unit circle. So that is happy. Okay, see you next time.